Let us verify Green's theorem for the integral x squared minus xy cubed dx plus y squared minus 2xy dy. So we want to verify Green's theorem for this integral. Here, whenever we say Green's theorem, we need a curve to be a closed curve. In this way, in this case, we are given a closed curve to be the boundary of a square with the vertices 0, 0, 2, 0, 2, 2, comma 0, 2. Let's draw the square. And we have a square. Let OA, BC be the vertices of a square. Let us further, we are also, of course, O is having coordinate 0, 0, A is having coordinate 2, 0, so we know that distance between O and A must be equal to 2 unit. In other words, a square is having length and breadth all equal to 2 unit. Now we should note that we want to verify Green's theorem, so we need the curve to be a not just a closed curve but closed as well as directional curve, and that direction must be in anti-clockwise direction. So from O to A we traverse, and then from A to B we traverse, and then from B to C we traverse, and then lastly from C to O we return back to O. We note that this direction is in anti-clockwise direction, so we can apply Green's theorem. Okay, next we have anti-clockwise direction. Next, let's state the theorem, or rather let's write the formula corresponding to Green's theorem that we want to verify. The formula is integral over closed curve f1 dx plus f2 dy equal to integral over region del f2 del x minus del f1 del y dy dx. We can write dx dy or dy dx depending on the circumstances or desire. We will prefer dy dx, but we should always cover the region completely. So here in this case we have got E to be the square and C to be the closed path OABCO. Now it's easier to compute right hand side rather than left hand side, so let's compute right hand side first. Oh, before that we should know what are f1 and f2. Now we are given as per the question integral over closed curve. Let's look at the question. X square minus xy cube plus y square minus 2xy. X square minus xy cube plus y square minus 2xy integral over closed curve. X square minus 2x minus 2xy cube x square minus 2xy cube dx plus y square minus 2xy dy. Let's compare this with the formula. We have f1 dx plus f2 dy, and in question we have x square minus 2xy cube plus y square minus 2xy dy. Obviously we should choose f1 equal to x square minus 2xy cube and f2 equal to y square minus 2xy. So we take f1 equal to x square minus 2xy cube, f2 equal to y square minus 2xy. Then If we want to compute RHS, then we need to compute del f to del x minus del f1 del y. Let's compute that. This implies del f2 del x minus del f1 del y. Del f2 del x minus del f1 del y equal to del x of f2. What is f2? Y square minus 2xy minus del y minus del y of f1. f1 is x square minus 2x y cube. That is equal to, now if you are differentiating partially with respect to x, then you will treat y as a constant, and x and y are independent of each other, so partial differentiation of y square with respect to x is just 0 minus 2, again y is a constant, del x of x is 1 minus, once again partial differentiation of x square with respect to y is 0. So 0 plus, we are differentiating partially with respect to y, so 2x is a constant, and differentiation of y cube with respect to y is 3y square. So that's equal to 6x y square minus 2y. Okay, so we have that much. Therefore, right hand side of Green's theorem formula equal to integral over region del f2 del x minus del f1 del y del f1 del y dy dx. That is equal to region. In the region, we observe that y is changing from 0 to 2. Since it is a square, if we change y from 0 to 2 and if we change x from 0 to 2, we will be exactly covering the square. So we will change y from 0 to 2, 6xy square minus 2y. This is what our partial derivatives, difference of partial derivative that we have computed just now. Dy dx as it is. This is equal to 0 integral 0 to 2. If you are integrating with respect to y, you'll treat x as constant. So 6x is just as a constant. Integral of y square is y cube by 3 minus integral of 2y with respect to y is y square. We will change y from 0 to 2. Let's put the upper limit and lower limit. So this is equal to integral 0 to 2 integral from 0 to 2. We can cancel 3 and 6 to get 2. So 2x, if you put upper limit 2, you get 8 here. And if you put upper limit there, we'll get 4. Lower limit is 0 dx. So this is integral of 16x minus 4, that is 16 into x square by 2 minus 4x. Let's put upper limit and lower limit here, and we have 8 into x square, and that 8 into 4, that is 32, minus 4 into 2 is 8, and that is equal to 24. Alright, this is the right hand side of the form. We have computed the right hand side. Let's compute the left hand side. For the left hand side, we need to evaluate over a closed curve, but the closed curve that starts from O and ends in O consists of 4 line segment. So let's write it down. Closed curve on which we need to verify Green's theorem. OA BCO consists of, I think it will have been more better to say, directional closed curve. Directional closed curve OA BCO consists of OA, comma AB, comma BC, comma CO. So if we want to compute the left hand side, then we need to compute line integral on each of those cases. Case 1, along OA. Okay. Well, along OA, we simply have it that equation of line OA is y equal to 0. So if you are integrating along OA, then obviously equation of line OA is y equal to 0. At the point O, the starting point, x equal to 0. At the ending point, we have x equal to 2. Alright. Let's integrate along OA. Along OA, comma, we have y equal to 0, and your starting point is x equal to 0, ending point is x equal to 2. So starting point of the integral is x equal to 0, ending point is 2. Since y equal to 0, dy is also 0, so that implies f1 dx plus f2 dy, integral of f1 dx plus f2 dy along OA. Along OA, integral of f1 dx plus f2 dy is simply equal to integral 0 to 2 along OA, what dy is 0, so dy we don't have to compute. What about f1 dx? F1 dx that we need to compute. And what is f1? F1, where is f1? F1 is x square minus 2xy cube. Let's write the value of f1. X square minus 2x y cube, but y equal to 0, so that is equal to integral 0 to 2. We know that along OA y equal to 0, so this is just x squared dx, and that is equal to x cubed by 3, and we need to integrate from 0 to 2, and that is just 8 by 3. Okay, so we have along OA integral is just equal to 8 by 3. So case 1 completed. Let's do case 2. Case 2, that is integral along case 2 along AB. Let's look at the figure, or rather the square. along AB, the equation of line AB is x equal to 2. And at A we have y equal to 0, and at B we have y equal to 2. So y will change from 0 to 2. Y will change from A to B, that is from 0 to 2. X will remain fixed and equal to 2. So let's write down along AB, comma, y will change from 0 to 2, x will remain fixed, x equal to 2. When x remain fixed, dx equal to 0. So once again, integral y changing from 0 to 2 along AB. If you are computing the line integral along AB, y will change from 0 to 2. F1 dx plus F2 dy. We are computing the integral along AB, so y will change from 0 to 2. Dx is 0, so F1 dx is 0. F2 dy. So what is our F2? F2, did we compute somewhere? Did we find somewhere F2? Yes, y square minus 2xy. Value of F2 is y square minus 2xy. So F2 dy, y square minus 2xy dy. But again, what we have is x equal to 2. So this is just integral y is running from 0 to 2 and x equal to 2. So y square along the line AB, the value of x is always 2. So 2 into 2 is 4, y square minus 4y dy. Let's compute this value. Y square minus 4y, if we integrate it, we will get y square is y cubed by 3. If you integrate 4y, you will get 4 into y square by 2. 4 into y square by 2. And if we can cancel that out, y is changing from 0 to 2. And if you write the value, we have 8 by 3 minus 8. And that is equal to minus 16 by 3. Okay, so we are done along OA, we are done along OB, AB. Next, we should do along, we are done along OA, we have done along AB. Next, along BC, from B to C. The line BC, the equation of line BC is y equal to 2. And we at the point B, that is we are starting from B to C. At the point B, we have x equal to 2. At the point C, we have x equal to 0. So we should start from x equal to 2 and end at x equal to 0. And throughout the line BC, we have y equal to 2. So our integral should start from x equal to 2 to x equal to 0. Case 3. Case 3 along BC. Along BC, comma, y equal to 2. In fact, equation of line BC is y equal to 2. And our integral, so line integral over BC integral over BC f1 dx plus f2 dy is integral over BC f1 dx plus f2 dy is equal to x is changing from 2 to 0. X is changing from 2 to 0, integral of f1 dx plus f2 dy. But since y equal to 2, dy equal to 0, so this integral is simply equal to 2 to 0, dy is 0, so that we need not compute something dx, and that something is f1. Where is f1? f1 is x squared minus 2xy cube. f1 is x squared minus 2xy cube. x squared minus 2xy cube. x squared minus 2xy cube, and y equal to 2. Along BC, y equal to 2. Let's write that. So this is integral 2 to 0 x squared minus x squared minus along BC we have got y equal to 2. So 2 cube is 8. 8 into 2 is 16 x dx. If we integrate x squared, we'll get x cubed by 3. And if you integrate 16x, we'll get 8x squared. The limit changes from 2 to 0. Lower limit is 2, upper limit is 0. Why is it so much fun there? Limit changes from 2 to 0. 2 to 0. So let's put that limit. Upper limit is 0, lower limit is 2. 8 by 3 minus 2 into 2 is 4. 4 into 8 is 32. That is equal to 8 take common, 88 by 3. We get it to be equal to 88 by 3. So we have computed case 3 as well. We got it to be 88 by 3. Case 2 we got it to be minus 16 by 3. Now last case. Last case along, that is your case 4. Along, we have started with OA, then AB, then BC, lastly along CO. Let's look at the figure. Along CO, here we are starting from C, and at the point C we have y equal to 2. We'll start from y equal to 2 and we'll end at y equal to 0, and the equation of line CO is x equal to 0. Wow, x equal to 0. So we have x equal to 0. We will start the integral from y equal to 2 and we'll end at y equal to 0. Along CO we have x equal to 0, and we will start the integral at 2 and end at 0. Your x equal to 0, so integral is integral over CO f1 dx plus f2 dy equal to, we start at C, that corresponds to y equal to, at C that corresponds to y equal to 2, and at y equal to 0, and since x equal to 0, dx is 0 plus f2 dy. What is the value of f2? F2 is just equal to y square minus 2xy. So F2 is y square minus 2xy dy. Once again, x equal to 0. So this is just integral from 2 to 0 y square minus 0 dy, and that is equal to y cubed by 3. Integral of y square dy is y cubed by 3. Let's write the lower limit and upper limit, and we have that equal to minus 8 by 3. Alright, so we have computed all the um, 4 cases, and let's write the result. Now integral over O A B C O, whatever be the function, integral over OA B C O equal to integral over OA plus integral over AB plus integral over BC plus integral over CO. Integral over OA, we have computed it to be, in case 1 we have done it, we got it to be 8 by 3. Integral over OA is 8 by 3. Integral over AB is minus 16 by 3. 8 by 3 minus 16 by 3. Let's write those two values equal to 8 by 3. 8 by 3, then over AB it is minus 16 by 3 over BC, integral over BC. Integral over BC is 88 by 3, and integral over CO is minus 8 by 3. Let's write those as well. Integral over BC is 88 by 3, integral over CO is minus 8 by 3. So we can cancel 8 by 3 out, and we have got 88 minus 16 by 3, that is equal to 272 by 3, and that's equal to 24. Bingo! We have got left hand side equal to 24, and also right hand side is also equal to 24. We have computed it long time back. Let's see once again. Did we do it? Yes, we have. Right hand side is also equal to 24. So we have basically verified Green's theorem. But we have done only for this curve, that was a square, and we have started from O, we have traversed to A, then we have traversed to B, then we have traversed to C, and then returned back to O, and we are given that particular function.